Hello everyone, I am Chanchal Shelar. My roll number is 2143. I am here to present my ISE activity of solid mechanics, which is based on wing deflection and aeroelasticity problems in modern aircrafts. Let's see further. The title is Wing Deflection and Aeroelasticity Problems in Modern Aircrafts. Firstly, we will discuss what I am going to present. Firstly, what is the title of the presentation? The introduction, what exactly wing deflection and aeroelasticity problems in modern aircraft means. The title, the basics of wing deflection, what exactly wing deflection means, and the aeroelasticity problems in these modern aircraft. Aeroelastic problems include the divergence, control reversers, flutter. We will discuss this in upcoming slides. What are the modern aircraft challenges and the solution mitigations and future research and conclusion? Let's see further. Firstly, we will see introduction, what exactly my PPT is about, what exactly my topic is about. Aircraft wings are not completely rigid. They are designed to be flexible structure. Aircraft wings are not, as we know, as we deals with the different aircraft, they are not exactly rigid. They are flexible type of structures. When an airplane is in flight, the aerodynamic forces when an airplane is in flight, the different aerodynamic forces acts, which mainly results in lift of an aircraft, causing them to bend upward, which is when the wing is flexible, the different forces causes them to lift upward because of there is a bending moment, the deflection of the beam. A small amount of deflection is normal and safe, but if the deflection becomes too large, it can lead to serious stability or control problems. There are some deflections in the wing due to some aerodynamic forces and dynamic forces. Due to this, the deflection is good for lifting the wing, but sometimes the more deflection can causes more stability problems for the aeroplanes, and the various control problems may have more issues. This interaction between aerodynamic loads and the elastic problems of the aircraft is known as, basically, these air flows and these flexibility problems and these air fluids, how fluids react and how the structures are made. This overall is called as aeroelasticity. Aeroelasticity also includes the effect of inertia forces, which together create complex behaviors. See, basics of wing deflection. What is wing deflection? Wing deflection is a bending or flexing of an aircraft which, under the influence of aerodynamic forces, there is a bending or flexion of an wing due to some aerodynamic forces. It's called as wing deflection. When a plane is in flight, the wings generate lift to support the weight of the aircraft. As we know, when the aircraft takes the flight, then there is some forces act on it. As the shape of the wing is like this, there are some forces acting on this. This is the Bernoulli's principle. As these forces act on this, which creates the lift. This lift forces causes wings to bend. This is in for the lift of that particular aircraft. Next, second one is, what do wings deflect? Why do wings deflect? Why there is a deflection in wings? Wings are not completely rigid. As we seen in the plus side, wings are not completely rigid. They are built with a material like aluminum and carbon composites, and wings are made with different materials like carbon and aluminum. Mainly aluminum is used widely, as it is more flexible than other metals, that allows some flexibility. If wings are too rigid, they could crack or break under stress. If we will not make the wings of the flexible material, it may cause more damage to the aircraft. It may directly break. Control flexibility makes them safer. This flexibility makes the airplanes more safer. Safe versus unsafe deflection. A small amount of deflection is safe or unexpected. A small amount of deflection is safe and expected. Modern airlines are wings are bent several meters without damage. This flexibility reduces the damage of an aircraft. We will proceed further. We will see the aeroelasticity problems. First is the static aeroelasticity problems, and second one is dynamic aeroelasticity problems. Here the static aeroelasticity problems. Here the structure bends or twists because of the steady aerodynamic forces. Here basically there is a steady aerodynamic forces. No vibrations are included. No deformation of the shapes. Firstly, in static aeroelasticity, first is divergence. Divergence is the basically the twist or more due to the lift. This twist keeps increasing until the wing can break, as there is a divergence due to which breaks the wing. Control effectiveness, basically control effectiveness is a measure of how effectively the control surfaces of an aircraft like ailerons, radar, elevator works effectively. Wing deformation, as the wing bends upward, the lift distribution changes. This affects performance and stability. Wing deformation, as the lift bends upward, this due to high bending can destroy the wing, or it can resulting into lift may changes of the aircraft. The second one is dynamic velocity. Here there is a changes due to motions and different aerodynamic forces acting on it. Dynamic response, when the aircraft hits a gust of wind, when there is a strong wind or turbulence, the wings shakes. These vibrations caused due to sudden load and wings inertia doesn't grow forever and adds extra size, which adds the extra size, which leads to more deflection of the wings. Flutter is a which is one of the dangerous one, in which various forces act together and leads to the vibrations of that or dumping of that airplane wing, resulting into more oscillations and resulting into more damage of that particular wing. Talking about the modern aircraft challenges, as we know, modern aircrafts are built in a very high technologies. In modern aircrafts, high speed and lightweight aircrafts, aerodynamic problems are more critical because wings are made longer and thinner to improve fuel efficiency, which makes them more flexible. As we know, as we have more technology, we need thinner aircrafts, we need short aircrafts to make the work more easier. Use of lightweight composite materials reduces weight but increases flexibility. Use of the lightweight materials uses lightweight composite materials reduces the weight, but it also increases the flexibility, which we want as our generation wants. Higher flight speed increase aerodynamic forces, making aeroelastic effects stronger. As we know, higher flights need more aerodynamic forces, more effectiveness of the aerodynamic forces, which results into good flight and the stronger effects on. As we know, stronger effects leads to various damages of that wing. For this we should know proper aerodynamic study, how to handle these problems. Let's see some real life problems of how wings deflect and how forces act on these wings. Let's see one of the example. Model a wing as a simply supported beam of span 20 meter. As we take example of a wing having the length of 20 meter. The wing is loaded by a uniformly distributed load, means the net aerodynamic force, which is equals to the 3500 Newton per meter, acting downward along the span, means this is the wing. Then the UDL is acting upon this wing, which is having the length of 20 meter. The UDL is 3500 Newton per meter. Two engine points loads, and two engine point loads are taken as P1 and P2, which is acting. P1 is of 25,000 Newton, which is acting at X1, which is distance of 5 meter, and P2 is acting at 13 meter, which is of 20,000 Newton. Measured from the left support A. From the left support A, uh, supports simply supports at A. Left is A is at x is equal to 0 and B is at x is equal to L, which is 20 meter. Our task is firstly to find the support reactions Ra and Rb. Second is to derive precise expressions for shear force and bending moment. We have to derive the expression for shear force and bending moment. Evaluate V and M at the key points. We have to evaluate the shear force and bending moments at these key points given. Key points like 0, 5, 10.21, 13 and 20. Find the location and value of the maximum bending moment, and we have to find the location and maximum bending moment value of the maximum bending moment. Let's see the equation answer. We have plotted here one diagram in which we have shown the length of the wing is 20 meter, which is from x to n. Then the RA is acting at the left side and RB is acting at the right side. Acting at the right side. Here P1 is given, P2 is given, and the uniformly distributed load, which is of 3500 Newton per meter, is given. Firstly, we have to find the support reactions. Firstly, total uniform load we have is 3500. Then we consider the point load at the. It will act at the center, which will act at the 10 meter. Take moment. It will take moment at point. As we know, moment at any point is zero. We take moment at point A, then minus P1, because it is going in downward directions. According to some books we referred, we will take it as a minus in downward direction. Then P1 into 5, P1 is at 5 distance, P2 is at 13 distance in 13. W means the point load acting. We have considered the utilized as a point load, which is at the 10 meter, and RB is into 20. It's on the overall span. Then from this moment equation we will get the RB force, and taking the vertical forces equilibrium, then RA and RB are acting upwards and all other three forces are acting downwards. By taking the summation we get the value of RA as we know the other values that we know. We will get the value of RB and RA from these equations. Later, take our task 2 is to derive piecewise expression for shear force and bending moment. We have to derive the expression for shear force and bending moment. Beam setup, we have taken the beam setup as we have given these points, and we have found the RA and RB reactions. Then see the shear force equation. We know that shear force is taken at any point at considering the distance of the point of the from the fixed end, as this is a simply supported beam. Then we get the equation as 60750. This is one is the 60750 is the RA value, and 3500 is the UDL acting on it. 2500 is the P1 at x is equal to 5. Basically, U is the deflection taken from the wings, and the 20,000 is the P2, which is acting at 13 meter. Bending moment, for the bending moment we consider the various movements along that beam. For this 6050 is the reaction at point A, which is acting at point X. We can consider X as different values as we have assigned in the equations. And here 2500 is the P2 and there is a P1 and P2. Step 3. Now we have to evaluate the value of x at 0, 5, 10.21 and 13. Then we take deflection. Then we get, when we put x is equal to 0, then we get value of v is 60750 Newton, and momentum at point x is equal to 0, we get momentum 0. When we take at x is equal to 5, when we get equation as we get shear force as 18,250 and bending moment as 26,000 to 2,60,000. At x, when we take at x is equal to 10.21, we get shear force as 22.15 and bending moment as we get bending moment 130250. At point x we get shear force as minus 2950 Newton, and at point x is equal to 0 we get shear force as this, and bending moment as this. Computing this, we have computed here all the data given here, final answer summary. We have taken these distances as x is 0, 5, 10.21, 13 and 20. We get a shear forces value here, which is in Newton, and the bending moment value, which is in Newton per meter. And we have to calculate some cases that x belongs to 0 to 5 and x belongs to equal to greater than equal to 5 and smaller than 13. And we have some cases. From this you get to know that here when we put the value from when we get x is 0 to 5, then we get x is equals to 17.36, which is no zero crossing in this region, where we don't get any zeros. In the second condition, x is smaller greater than equal to 5 and smaller than 13, we get x is equals to 10.21. This point is valid inside the beam between the, which is exactly at the point, means we need a deflection at the center maximum, or at, or from minor distance from the center, then this point is valid. And the third case, in this we are getting the we are not getting the valid point. Considering that point, we get that v of x is equal to 0 is x is equal to 10.21, and for bending moment we get x is equal to 10.21, as that's the valid condition. Then we get bending moment as 307,630.3 Newton per meter. From this, we get the maximum bending moment location. At the maximum bending location is as 10.21 meter, and the maximum bending moment value, the value for the bending moment is 307,630.3. For these forces, we have taken the diagram, shear force and bending moment diagram. The above diagram is of shear force and this below diagram is of bending moment. The shear force diagram is from here to here, and the shear force is becoming negative at the end points, and the bending moment diagram is given here. Conclusion. From the problem based on the beam deflection, we observed how external reactions and bending moments and the deflection structure make the structure more effectively, and how these deflections make the lift of that aircraft more effective. This simple analogy helps us understand how wings of an aircraft are designed and how it behaves under different conditions, how it works under different aerodynamic conditions, and how lift is generated. The beam deflection problem not strengthens the understanding of structural mechanism but also directly connects to real world problems. By these problems, we also directly connect to the real world problems and check how the wing can deflect at in any forces, how much force we can calculate, and how much force if we give, then how much deflection we can get. From this, we can predict how the stable the aircraft is, how the airplane is stable, and we can predict the performance of these aircrafts by taking these theoretical values, and we can perform various experiments on this, and we can perform how stable the aircraft is, we can predict from this. That's it, my presentation. Thank you.